Okay, so we have this function, and we want to find all of these things: the intervals of increase and decrease, the local maximum and local minimums, the intervals of concavity, and the inflection points. So A and B, remember the way to find these is using the first derivative test. And the inflection points and intervals of concavity, this is, it's basically the first derivative test. It's the same exact process except that you use the second derivative. Because remember, the second derivative is the one that tells you whether the function is concave up or concave down. And the inflection points that's simply a point where the concavity changes. Okay, so let's do the first thing. Well, to find part A, we're going to need to find the first derivative. So the first derivative is just 12x squared plus 6x minus 6. And to do the first derivative test, what we need to do first is find the critical points. So remember, to find the critical points, we're going to set this the derivative equal to 0, and we're going to solve this equation. So the first thing is, well, we notice that we can factor out a 6, and this will make the factoring a lot easier. So we would have 2x squared plus x minus 1 equals to 0. And if we take a look at how to factor this, well, we know we need a 2x and an x, and then we would need a positive 1 and a negative 1. And this works because 2x times 1 is 2x, minus 1x would give me that x in the middle. So I have two critical points here. One is x equals positive 1/2. The other one is x equals negative 1. These are my two critical points. And I found them by setting the derivative equal to 0 and solving it. Okay, now once I have that, then I can find the intervals of increase and decrease and the local maximums and local minimums. A and B is kind of the same step for both of them. So we'll put B here, but we realize that it's really all part of the same thing. So here we're going to first set down our critical points. So we're going to have negative 1, and then we're going to have 1/2 right here. And we're going to test in between these values. So here to the left of negative 1, I'll pick negative 2. Between negative 1 and 1/2, I'll pick 0. And after 1/2, I'll just pick 1. And remember, the idea is that you're going to plug in these test values inside of the derivative, and you want to see whether it's positive or negative. The reason why is because if the derivative is positive, that means the function is increasing. If the derivative is negative, that means the function is decreasing. And that's how you find the intervals of increase and decrease. Okay, so let's do this. Let's try negative 2 first. So we're going to plug it into the first derivative, remember, because we're looking for whether it increases or decreases. And all we care about is the sign, really. So if we plug in negative 2 into the derivative, which is over here, we would get 12 times negative 2 squared plus 6 times negative 2 minus 6. Okay, so this is going to be 12 times positive 4, which is 48, minus 12, which is 36, minus 6 is positive 30. And again, really all I care about, it's not really the number, it's the sign that I'm interested in. So the sign is positive, that means This guy is positive. That means my function is going to be increasing. I'm going to label increasing by a big fat blue arrow going up. Okay. So once I have my big fat blue arrow, I need another arrow. So I'm going to plug in 0. So the same thing. Plug in 0 into the derivative. And if I plug in 0 into the derivative, I would get -6. So this number is negative. That means my function has a negative derivative right there. That means that it's going to be decreasing from -1 to 1/2. Okay, and then the last one, let me do it over here. Split this up. I'm going to plug in my other test point, 1. So the derivative at 1 is equal to 12 times 1 squared plus 6 times 1 minus 6. This is equal to positive 12. So this is a positive. That means the derivative is positive after 1/2, which means that I draw a big fat blue arrow facing up, and that means that my function is increasing. Okay, and then, so remember what this tells you about the local maximums and minimums. This is basically the first derivative test. Notice that because at -1, my function is first increasing, and then after -1 it starts decreasing. That means that at -1 I have a local maximum. At -1. And then to find the y value at that local maximum, I would just have to plug the x value into, this time, the original function. So when x is equal to -1, y is equal to 4 times -1 cubed plus 3 times -1 squared minus 6 times -1 plus 1. So this is equal to -4 plus 3 is -1 plus 6 is 5 plus 1 is 6. So this means that I have a local maximum at the point -1 and y is equal to 6. Okay, and then applying that same reasoning at 1/2, notice what's happening is that my function is decreasing, and then it's increasing after 1/2, and so that means that I have a local minimum at x equals positive 1/2. And then to find the y value, it's the same idea as up here. I'm going to plug that into the original function. So 4 times 1/2 cubed plus 3 times 1/2 minus 6 times 1/2 plus 1. And this is equal to -3/4. So this means I have a local minimum at the point 1/2 -3/4. So these two, this answers part B of the question, the local maximums and the local minimums. Okay, and then to find the intervals of concavity and the inflection points, I basically do what I just did for the first derivative, except that I'm going to do it for the second derivative. So the first thing I need to do is I need to find the second derivative. And to find the second derivative, well, I just get the derivative of the first derivative, which is going to be 24x plus 6. And remember that you just set this guy equal to 0, and this is going to give me my possible inflection points. So if I set this equal to 0, that means x is going to equal negative 1 over 4. And this is a possible inflection point. Okay, so then to figure out if it is an inflection point and if it changes concavity or not, we do the number line exactly like we did here, except that this time we only put one value, which is our possible inflection point. So we put our possible inflection point right here, and then on each side, again, just like we did here on the first derivative test, we're going to do a similar situation where we pick test points on either side of negative 1/4. So on this side we can pick negative 1, on this side 0, and that should give us some easy answers. So let's plug in the first one. If I plug in negative 1, I'm going to plug it into, this time since I'm looking for the concavity, I'm going to plug it into the second derivative, because that's the one that tells me whether my function is concave up or concave down. So if I plug in negative 1, I'm going to get 24 times negative 1 plus 6. This is negative 18. So negative, that means the second derivative is negative in this area, which means that my function is going to be concave down. It doesn't mean it's decreasing, it just means it's concave down in this area, because that's what the second derivative tells me. Okay, now if you do the same thing with our other test point, 0, what we're going to get is that the second derivative at 0 is equal to 24 times 0 plus 6. This is positive 6. So the fact that this is positive after negative 1/4, that tells me that my function is going to be concave up after negative 1/4. And so that means that this, which was a possible inflection point, is in reality, it is an inflection point, because it does change concavity. It goes from concave down to concave up. So to find the actual inflection point, what we have to do is plug in the x value back into the original function, because that's the one that gives us the y values. Okay, so we're going to do that. So when x is equal to negative 1/4, y is equal to 4 times negative 1/4 to the third plus 3 times negative 1/4 squared minus 6 times negative 1/4 plus 1. So it's very important to realize why we plug this the negative 1/4 back into the original function. The reason why is because we're looking for the y value. The original function, when you plug in an x value, it'll give you the y value at that point. If you plug in an x value into the first derivative, it'll tell you whether the function is increasing or decreasing. If you plug in an x value into the second derivative, it'll tell you whether it's concave down or concave up. And that difference is really important to understand. Okay, so going back here, if we plug all this in, we're going to get 21 over 8. Okay, so that means that my inflection point is going to be the point -1/4, 21 over 8. And that's it. I found everything. I found that my function is increasing from -infinity all the way to -1. And also from 1/2 to positive infinity. It's decreasing from -1 to 1/2. And then my intervals of concavity, it's concave down from -infinity up to -1/4, concave up from -1/4 to positive infinity. And that's it.